started chapter 7 last time, we're learning about estimators. What's an estimator? What's that, Kate? So that would be, right, if I'm going to estimate a population mean, you're right, I might use a sample mean to do it. That's what's called a point estimate. That's right, that's a good example. What else did we learn about besides point estimates? Confidence intervals, right? You can estimate with a point, or you can estimate with a whole interval. And we talked about how there's a confidence level that goes with that. Yeah, so this is good. These are things we learned here in chapter 7. Now, let's think about what we did. Section 7.2 that we covered last time was estimating a population what? It wasn't a mean. What were we estimating last time? Proportion. So when you guys go to do the homework, yeah, now we have 2 assignments, don't we? Well, the first assignment will be on proportions. And I'll post the video so that you guys can look at what we did last time as you're doing the homework. But then today we're going to talk about how to do a population mean. Now I said I'm kind of skipping section 7.3. Section 7.3 has almost exactly the same title, except for one part of the last word. Section 7.3 is if you know sigma. What does sigma stand for? Standard deviation of the population. When I said it's unrealistic, how could you possibly know the standard deviation of the population if you don't know the mean of the population? Don't you need that in the formula to compute the standard deviation? I guess it depends which formula you used. So it's just very unrealistic that would ever happen. That's why I don't mind skipping it. Okay. So now the book says, well, let's do it when sigma is unknown. How do we estimate a population mean? That's what this is about. Okay, key concepts. Number 1. I think you already do that, right? Best point estimate of mu is, what's that? Yeah, that's mean. What kind of mean? This is the sample mean. If we're trying to estimate mu, the population mean, which is what we're trying to do, the best point estimate you can get is x bar. I didn't really say exactly what I mean by best yet. I'm going to do that on the next slide. Second key concept, how to construct a confidence interval. And what? How to interpret confidence intervals. Didn't we go over that last time? We did, for population proportions. Now we're going to do it for population means. So, point estimates, confidence intervals, and then number 3 on the key concepts is how to determine the sample size necessary. And didn't we do that last time we were here with population proportion? What's the letter that stands for sample size? No, little s stands for standard deviation of the sample. N is the sample size. And the way we did this last time was that we did algebra on a formula containing n. Right? If I can get n by itself, then I'll have a formula for the sample size. Okay, now I'm really pushing my luck, but I'm going to try it, because I think it's good to review before you move on. What formula had n in it last time? Margin of error. Do you remember what the letter was that stood for error? Capital E. Remember we had capital E equals something? Well, today we're going to have capital E equals something also. But it's a little bit different because we're doing means now instead of proportions. Okay? Again, I do not care that you remember the formulas. I care that you remember the ideas. And that's why I'm pointing this stuff out. Because the same ideas we did last time is exactly what we're going to be doing today. So I think that's really important to understand. Okay. Now, sample means. Here are two big statistics words. Unbiased. Don't write all this down. If you want to write any notes down from this slide, write down X bar is unbiased. And you might write for number 2, for many populations, X bar is more, and here's the other stats word, consistent. What does that mean? Well, those are two big statistics words, okay? So, when I say unbiased, okay, here's what it means. Unbiased means the distribution of sample means is centered around mu. Right? We're trying to find mu. Here's mu, but I don't know where it is. Mu is somewhere on the number line. Right? Because it's a number. It could be the average, what? I don't know. Average temperature we're trying to find. So if we're trying to find the average temperature, what we could do is take a sample of temperatures. Right? When I take a sample of temperatures, I could get, say, 4 of them. That'd be size 4, then n equals 4. Then I could compute the mean of those. Do you think the mean of those will be the same as mu? No. Could it be bigger? Sure. Could it be smaller? Sure. What point number 1 is that if you plot lots of the sample means, mu is going to be the center of that distribution. Mu will be near the center. Does that make sense? Okay, and actually we saw that, right? We saw that. We saw a nice little bell curve with mu as the center. Okay, what the heck does point number 2 say? Point number 2 says consistent. To do consistent, I need 2 pictures. Okay? So let me draw 2 bell curves. Here's a bell curve. And here's a bell curve. Now, at the center of each bell curve, I know I'm going to get mu, because that's point number 1. Think? Now, what's the difference between these 2 guys? Well, I would claim that this curve is what we call more consistent. You know, you might even draw this curve higher. Higher, but thinner, right? Because most data is closer to the center. That's what I mean by more consistent. Here, we have more variation in the sample means? Or in the sample stats? What point number 2 is saying is that, look, if you take x bar, you're going to get a curve that looks more like this and less like the one on the right. And we would rather have one on the left. Does that make sense to people? Yeah, so that didn't make sense, so I'll try again. What are we trying to find? We're trying to find mu, right? The population mean. I'm catching it with a net. The net was my confidence interval, right? Which kind of net would I rather have? A small net or a big net? Well, I guess in some ways I'd rather have a small net if I know I'm going to catch it. Because if I have a small net, then there'll be less places to look for it once I caught it. So by consistent, what I'm saying is you're more likely to get most of the data close to the center. A shape like this. That's more consistent. This, more variation. See, more consistent means less variation. So I repeated it kind of. Did that help? Yeah. So one thing we're going to start doing in the book is say, well, when can you do these things? What are the requirements? Okay, 2 requirements we need. Number 1, need a simple random sample. We went over that like I think the first week of class, what the heck that is, right? So you're going to need a simple random sample. And then question 2, or the second requirement, it says population is normally distributed or n bigger than 30. Why would this be good enough? Why would n bigger than 30 be good enough? Greg?
Bigger than 30 is considered to be a large size, correct?
Yes.
And so, does that have anything to do with how much data you have?
Well, I guess. I guess when we did the example on the board last time, remember we were doing we took the mean of 4 digits and we started plotting over on the right? And we were trying to demonstrate something. Do you remember what we were trying to demonstrate? That they tend to go towards a bell curve, a normal distribution. What's that theorem called, by the way? Central limit theorem, right? Central limit theorem says if you have n bigger than 30, the central limit theorem says they will be approximately normal. Okay? So sometimes we know the data is normally distributed. Sometimes we know that. Like, for example, IQ scores, the way they design the scores is they make a bell curve. Okay? That I know is going to be normally distributed. But if I don't have a normal distribution, as long as I have a big sample size, say bigger than 30 or 40 or something like that, the central limit theorem tells me it's going to look like a bell curve anyway. So I'm in good shape. Okay. Now, I need to talk about a new kind of distribution with you. And at first you're like, oh no. What kind of distributions have we studied so far? Normal, a probability distribution in general. This is going to be a distribution of you could call this a population distribution. But yeah, the standard normal and then the just normal in general, right? Okay, well this is kind of like a normal distribution. Actually, this formula looks familiar to me. Does it look familiar to you? When did we use it? central limit theorem, well, because this is kind of like the old formula. What was the formula for the normal distribution? Well, we wanted to do the normal distribution. We did, yeah, we did. X, now if I was using population, it would be x minus mu over sigma. I think you're right, I had x bar here and s there. But this is the normal distribution, right? Well, I guess when we did the central limit theorem, we learned if it's not normal, if n is less than 30, then you can use this, right? So this is what's called the t distribution. And I'll tell you that the t distribution looks a heck of a lot like the normal distribution. There's really only one thing it has that the normal distribution doesn't, and that's that little piece you're dividing by, right? We divide by the square root of n. That's the new piece. So this is a student t distribution for all samples of size n. It says it's used to find critical values denoted by t alpha over 2. Okay. We had a parallel to this last time. What was it we computed last time? Z alpha over 2. Why did you have to divide alpha by 2? Can someone explain that to me? There were two tails, right, to the normal distribution. Well, question, Julia?
What's
In between the t and the 2? Oh, it's alpha.
Okay.
T alpha over 2. Thank you for asking. And just like we used to have z alpha over 2.
Okay, good.
That's okay. So now, let me show you what they look like. Well, they look a heck of a lot like the normal distribution, don't they? I mean, can you even tell them apart? Well, the blue curve is normal. And then we're showing you some student t distributions. We're showing you n equals 3, that's in orange. N equals 12, that's in red. So it looks like as your sample size gets bigger, then the t distribution looks more like what? The normal distribution. Actually, I'd be curious to see apply. What if n equals 30 or 40? Something bigger than 30, I think it would look just like the normal distribution. So, that's the central limit theorem. But I'd be curious to see. Okay, that was from your book, that figure. All right, so now we're going to learn how to construct a confidence interval. This is the second thing I need to teach you. How do we construct a confidence interval? All right. So what's going to happen? We're going to pinpoint mu between two numbers. Between x bar minus e and x bar plus e. Right? And when it says confidence interval, that means I'm going to say something like, I want to be 90% confident, for example. Something like that. That the mean is in between these two guys. What's E called again? Margin of error. Oh, and look what we have here. We have a formula for the margin of error. Is that the same formula we had last time for the margin of error? Well, kind of, right? Let me think about last time. Matter of fact, when we had population proportion we were going for. So that was section 2. Let me write down what you have. Oh, timeout, timeout, timeout. Some of you are copying crazy copying down. I have to point something out here. This is a slide 7-3, which is not what I'm covering today. And why do I say this is a slide for 7-3? Because this is when sigma is what? Known. If I knew sigma, I'd put it right there. Okay? The population proportion example was z alpha over 2. And then wasn't it times the square root of p hat q hat over n? Wasn't that it? I think that was 7-2. Okay. So if we had 7-3, we would replace the square root of p hat q hat, we'd replace it with sigma. All right. So what are we doing now? Sigma not known. Okay. Not known. Well, if you don't know sigma, you could still get a confidence interval. It's going to, again, look like this. Right? Mu is going to be between x bar minus e and x bar plus e. What's the difference in the function? The error is going to be what now? T alpha over 2 instead of what? Instead of z alpha over 2. What else is different? What does this S stand for? Standard deviation of the sample. See, if you know sigma, you'll put sigma up there. But if you don't, you use the sample. And then you have to use the t-distribution. Okay, now, it says T alpha over 2 is found in table A3. That's in the back of the book. I'll show you where in a second. There's one other thing you need to know when you talk about the t-distribution. There is something called degrees of freedom. What the heck are degrees of freedom? Well, I'll get to it, but it's very easy to compute. Just take n minus 1. In a sense, that's going to tell me where to look on the chart. But I'll explain what it is in a second.
So is it separate?
Is what separate?
The degrees of freedom?
Yeah, this is just, this tells me how to compute T alpha over 2. Right? Because I said we're going to use this table. You need to know the degrees of freedom if you want to use the table. That's kind of how it works. When we do the example, I think you'll see. Okay, so it said listed below are 12 lengths of randomly selected movies in minutes. Okay? Fine. And there's tons of lengths of movies in the back of your book. It's one of the data sets. But they just took a sample here of size 12. You see that? Now, I guess my question is, do you guys understand what the problem's asking in Part A? Part A says, construct a 99% confidence interval estimate of, well, I'm going to write mu. Okay.
So if you want black, you want the middle to be, or you want the middle to be 99%, and then the two sides would be 0.045, like the alphas, is that what you want to say?
Well, it's like that, yes. But let me slow down a second. What are we doing? We are measuring lengths of movies. Right? We're measuring lengths of movies. It says construct a 99% confidence interval estimate of mu. Mu is the population mean? Okay. Tell you what, to get this going, I'm going to pause. I'm going to enter those 12 numbers into my graphing calculator, just in a list. You guys know how to do that, I think. I'll remind you if not. And then we'll come back and look at what we do with it. So the question is, what are we trying to find? I told you, this is, I think, hard to understand. I know it says we're trying to find mu, the population mean. What is that in this example? It is the average length of a movie. Of all movies, where? In the population. Now, I don't know what the population is. I guess it's everything in data set B, right? If you go to the back of the book, there's a lot more than 12. There's hundreds of movies that they wrote down the movie lengths for. That's my population. This is a sample from that population. Okay? Now, can I compute the mean of that population? Well, I guess you'd have to type in all that data and use a computer, add it up and divide, right? You could. Actually, you know where you could do? We could do it on StatDisk, because all this data is on StatDisk. It could compute the mean of the population for us. Now, I'll just tell you, because I already have it here. Let's see, do I have, no, I don't have the population mean, I'm wrong. We could do it on StatDisk if we want. But what I can do quite easily right now, since I entered the data into my calculator, what is it I can compute? The sample mean, right? So let's do that. See, in my calculator, let's see, I had just typed all 12 values into list 1. Now I'm going to hit second quit. And now I'm ready. And if I want to get some statistics on it, do you remember what we did? Hit the stat button, but instead of hitting edit, see, Julie, if you hit the stat button like this, it's on edit right now, but if I move one to the right, it goes to calculate. And I want to calculate my one variable statistics for everything in list 1. So I'm going to type one variable statistics, and then I'm going to hit second 1, and that tells it list 1. Now, if you don't type it, I think it does list 1 automatically anyway. But let me press enter, and it gives me all kinds of stuff that I might be interested in. Let me write down a few of the things that we might be interested in. Let's see. X bar. It tells me the mean for my sample is 121.75. Just over 2 hours, right? 120 would be 2 hours. What else did it tell me that I might be interested in? N is 12. I knew that, though. But you're right. N is 12 is important. What else? Yeah, now which standard deviation do I want up there? Is this a sample or a population that's in the calculator right now? This is a sample, so I want to use S, right? S equals 20.356481. 20.35, what was it? 64821? Oh, I don't care. I mean, the more digits I use, the more accurate my results will be. In a sense. Okay, what else? N equals 12. Is there anything else here that might be worth? Well, maybe the min and max might be nice to know, but I won't need those for these formulas. So I'll just say that, you know, we got some nice data here about the sample. What I hope is that the mean of the population is close to that. It's about 2 hours. Problem is, do I know that? No, I'll never know it. Maybe I picked a really bad sample. Like, I picked all the long movies. There's a chance that happened. That in general, most movies are shorter. Or in general, most movies are longer. Although I think you might agree, 2 hours, that seems about right for an average movie, right? Okay. Now, here's another big question, I think. Why would someone possibly want to do this? And I think that's answered in question B there. Read question B to yourself. Okay, so we have some information now. Now we should be able to construct the confidence interval. This is what the confidence interval is going to look like. X bar minus E, X bar plus E. I already have X bar, right? I have that, so I'm all set. Hey, I already have S too, right? And I have N. So the only thing left to compute is what? T alpha over 2. So I have to show you how to compute that. Last time, I showed you how to compute Z alpha over 2, but we still have to practice that. Maybe we'll go over that next. Okay, so how do I compute T alpha over 2? It says it's found in table A3. Okay. So table A3, you can find in the back of your book. If you open to the inside front cover, of course, this is the normal distribution, right? These are the Z-scores. But this page here, if you flip it over one page, just go back one more, you'll notice they have a picture of the T distribution. That's this. So the back page has the Z's, but if you flip back one more, that's the T's. It's also somewhere else in the appendix, table A3. But this is it. Okay? Now it says here, we are either looking for the area in one tail or we're looking for the area in 2 tails. All right, I have to try and explain this. Well, a confidence interval looks like this. X bar minus E less than mu less than X bar plus E. Okay? We're going to try and catch the population mean in my net. So what's it look like? Well, if I plotted the distribution, right? A T distribution, when I draw it, it looks a lot like a bell curve. I'm just going to draw the same thing. And what I want to have happen is I want how much of the area to be contained in here. I want 99% confidence interval. So I want 0.99 of the area to be in here. 0.99. Okay. So now, let's see what I'm doing. This is a tail, and this is a tail. How much area is in the area in these 2 tails? Well, if I say in both of the tails together, we know that has to be 0.01. So the area in each tail is what? 0.005. Right? Now, why do I bring this up? Because last time, what we did was, we found a Z value based on that information, right? We knew that this was 0.005, so you'd find the Z value for that. And this one is 0.005, so you'd find the Z value for that. Okay? Now that's not what I'm doing this time. This time, I'm doing this as a T distribution. So when you're looking on the chart, which column do I want to use on this chart? You guys gotta look at the chart, or you won't see what I'm talking about. Well, you can either use area in one tail as .005 or area in two tails as .01. Doesn't matter, right? It's the first column. You guys see me? See that? So we use the first column is what this tells us. First column of the chart. See that? We have to know the degrees of freedom, don't we? So what do we know about the degrees of freedom? It's always n minus 1. Now, why do I say that? I don't want to go into it now. I don't. I want to just say it's very easy. Look on the chart. It's basically how many variables you have left. You're kind of pinning one down as soon as you start using the t-distribution. But if we just look on the chart under, let's see, well, n is what in this example? 12. You're right, I did need that. So my degrees of freedom is 11. So now I think I have everything I need to compute E. So let me see if I can get my blue marker out and compute E. And again, the formula we're going to use was right here. D alpha over 2 times S over the square root of n. So let me write that down before I even start. E equals T alpha over 2 times the fraction S over square root of n. Yeah, df is going to be 11 for our example. So that means looking on the chart, what is T alpha over 2? Well, let's see. 3.106, right? What is that? That's the area of the black on the picture. No, it's not. I'm sorry. The area of the black is .005. What this is, it's the t value. It's like the z value. Yeah. So this would be 3.106, and that'd be negative 3.106 if you want. Okay. Now, try to compute the error. Error equals T alpha over 2, so we type in 3.106, right? Times what? Yeah, that 20.3564821, that crazy thing. Divided by the square root of what? 12. All right, now I'm ready. Calculator out. Punch that in. And go from there. 3.106 times 20.3564821 divided by square root of 12. That should do it. So my error was 18.25, basically. That okay? Okay. So now I'm ready for the confidence interval. We know x bar. That's, yeah, let me do it in red because I had those stats out before. So it's 121.75 minus the 18.25. And mu is going to be between that and 121.75 plus 18.25. Okay? That's my 99% confidence interval. So I guess my 99% confidence interval would be, looks like 103 and a half. And 140. That look okay? I'm 99% sure that the average length of a movie is between those values. And the manager might say that's no good. That's too wide a range. But what can the manager do now? How do we do part B? No, seriously, how are we going to do part B? Let's see, what are we asking here? Okay, what is the minimum time that a theater manager should plan, start times between movies, so that this will work for a typical movie? Well, what do you think? I'm sorry, what? No, yeah, we have to add 30 minutes to what? Well, let me ask you this. If you're the manager, do you think I should add 30 minutes to the minimum time or 30 minutes to the maximum time? Well, I guess I want more show times, but the other thing I don't want is to not have enough time to clean the theater because they won't come back, right? So, yeah, how you actually plan, I guess, is up to your managing style, right? But the idea is the average movie is between 103 and a half minutes and 140 minutes. So if I add 30 minutes to, say, the bigger of the two, then as long as I allot 170 minutes, should be enough time. Between start times for the average movie. Almost 3 hours, right? 180. So yeah, 170. This says you should allow 2 hours and 50 minutes between shows. So you're telling me that that's not what's done. You're telling me that is what's done. Yeah, I mean, good questions. I can't relate to this as well because I don't go to movies that often, but I know, you know, that's a lot. But I think of sporting events. We schedule sporting events. Say you're running a sports league, you got to plan when you're going to start the games. And I'll tell you, for basketball games, sometimes you don't know how long it's really going to take. You know, yeah, there's a clock, but the clock stops. There could be a lot of timeouts or a few timeouts. Maybe you go with an average and then add some extra time, kind of like this. This is a realistic problem, I